So let's take a look at double integrals over rectangles. So just a basic introduction here, a single integral, so let's say the integral of f of x dx, gives you the area under a curve. So double integrals, so let's say the double integral of a multivariable function, f of x y, so then dx dy, or you could also replace it with dA, which stands for the area, because if we're taking a look at a coordinate plane here, if we're trying to find the area of this rectangle, the x times the y distance will give you the area. So that's why dx times dy is the same thing as dA. So if a single integral gives you the area under a curve, the double integral will give you the volume of a solid under a surface. And that surface is the multivariable function. So in this video, we'll be basically using Riemann sums in order to estimate the volume of the solid, or estimate the double integral. Now, using Riemann sums, the formula for a volume of the solid is going to be the volume equals the infinite series from I equals 1 to m times the infinite series from I equals 1 to n of f of x sub ij, comma y sub ij, and then times delta A. Now, this formula might look very confusing at first, and obviously you don't need to memorize it, but what we're basically doing here is we're going to choose different coordinate points or different xy points, plug them into the given function. So let's say we have f of x1 comma y1, and then we have f of x2 comma y2, and then we have f of x3 comma y3. So just pick a handful of points. We're going to add those values together, and then we're going to multiply by delta A. And delta A is going to be the area within each individual region. And so that's all the formula is, and that's how we do the Riemann sum. Now you don't need to worry about I, and I'll explain a little bit more about what m and n are in a little bit. So for part A of the first question, we need to estimate the volume of the solid that lies below the surface z equals xy and above the rectangle given below. So use a Riemann sum with m equals 3, n equals 2, and take the sample point to be the upper right corner of each subrectangle. So realize that z equals xy is our given multivariable function. So we can also rewrite it as f of xy equals x times y. They're both the same thing. Now the rectangle R is given in set notation here as for all xy points such that the x values range from 0 to 6 and the y values range from 0 to 4. So if we were to draw this out in a coordinate plane here, once again the x values range from 0 to 6. We have 1, 2, 3, 4, 5, 6. And the y values range from 0 to 4, so 1, 2, 3, 4. So this is the rectangle that we create using this set notation here. So this is going to be the rectangle R. So now what we need to do next is divide up this rectangle into smaller rectangles. So now we're given the information that m equals 3. So m just stands for the number of subrectangles we need in the x distance. So if m equals 3, we need 3 rectangles in the x distance. So we have 6 units here. And so if we need 3 rectangles, each rectangle is going to have a width of 2 units. So we divided it up into 3 rectangles. And now n stands for the rectangles that we need in the y distance. So in the y distance, each rectangle is going to have a width of 2 since we have 4 units. So now we have divided this bigger rectangle up into 6 smaller rectangles. And so now it's telling us that we need the sample point to be the upper right corner of each subrectangle. So if I were to draw or label out the sample points here, we need the upper right hand corner of each rectangle or subrectangle. So 6 total points, each point is on the upper right hand corner. So now remember the formula that I gave earlier. All we're going to do is find out what each of these coordinate points are and plug them into the given function. So let's go ahead and first start with this point here. This point is just going to be at 2, 2. So we have f of 2, 2. Now plus the next point when we plug it into the function. So let's just go ahead and go with this point, which is going to be at 2, 4. So plus f of 2 comma 4. Now this next point is going to be 4, 2. So plus f of 4 comma 2 plus the next point here at 4, 4. Plus the next point here. This one's going to be at 6, 2. And then finally plus the last point which is at 6, 4. And remember, we're going to multiply the entire thing by delta A. Remember, delta A is going to be the area within each individual subrectangle. So the area within each one of these is simply just 2 times 2, which is 4. So we're going to multiply the entire thing by 4. So now let's go ahead and evaluate each of these. So obviously it's just x times y, the function. So we just take the x coordinate times the y coordinate. So 2 times 2, or f of 2 times 2, is going to be 4, plus f of 2 times 4, so that's going to be 8, plus f of 4, 2, so 4 times 2 is 8 as well, plus f of 4, 4, so that's going to be 4 times 4 is 16, plus f of 6, 2, so 6 times 2 is 12, and then finally plus 6 times 4, which is 24. So if I go ahead and I'll add all these up, we get 4 plus 8, 12, 12 plus 8, 20, plus 16 is 36, plus 12, 48, and then 48 plus 24 will give us 72. So then 72 times 4 is 288. So this is going to be the approximation of the volume of the solid that lies under the curve z equals xy, or f of xy equals x times y, using a Riemann sum. So now for part 1b, we need to use the midpoint rule to estimate the volume of the solid in part A. So the midpoint rule obviously is just another way to estimate the volume of a solid. Instead of using coordinate points from the upper right hand corner, this time it's the midpoint. So we're basically going to use the midpoint of each rectangle, or each subrectangle. So in this case, we're just going to take the exact middle of each subrectangle here, and then use those as our coordinate points. So let's go ahead and evaluate. So delta A obviously is still going to be 4, so we're going to multiply by 4. And let's go ahead and figure out what each of these coordinate points are. So right here, this is just going to be at 1, 1. So we have f of 1, 1, plus, right here, this is f of 1, 3, plus f of, right here, this is going to be 3, 1. So we have f of 3, comma 1, plus f of, right here, is going to be 3, 3, plus f of, right here, this is going to be 5, 1. And then finally we have f of 5, 3, right over there. So now when we evaluate f of 1, 1, when we plug it into the multivariable function here, we just multiply 1 times 1. So that gives us 1, plus f of 1, 3, which gives us 3, plus f of 3, 1, also 3, plus f of 3, 3, that gives us 9, plus f of 5, 1, that gives us 5, and then plus f of 5, 3, that obviously gives us 15. So now if you evaluate here, we get 4 times 1 plus 3 is 4, 4 plus 3 is 7, 7 plus 9 is 16, plus 5, 21, and then plus 15 will give us 36. So then 4 times 36 will give us a value of 144. So that is going to be the estimate for the volume using the midpoint rule. So now moving on to number 2, a contour map is shown for a function f on the square r equals, well, the x values range from 0 to 4, and the y values also range from 0 to 4. So for part A, we have to use the midpoint rule with m and n both equaling 2 to basically estimate the value of the double integral of f, or in other words, the volume of the solid given under the surface of f. And then for part B, we have to estimate the average value of f, and I'll talk a little bit more about that later. Now, looking below at this contour map, now I apologize for the drawing, I basically freehanded this, but a contour map basically shows, all these numbers basically show the value at the given lines. So if I were to redraw the region R, or the square R, so region R, or the square R, tells us that the x values range from 0 to 4, and the y values also range from 0 to 4. So 1, 2, 3, 4 in the x direction, and 1, 2, 3, 4 in the y direction. This is approximately the square that we have created. Now, it wants us to have both m and n equal to 2. So once again, m is the number of subrectangles in the x direction. So we just need 2 subrectangles. So the width of each rectangle is going to be 2 in the x direction. And the same thing in the y direction. The width of each one is going to be 2. So we basically created 4 equal subrectangles. So now the problem asks us to use the midpoint rule. So once again, for the midpoint rule, we're going to take the midpoint in each one of those smaller squares, so the exact middle, and then we're going to find out what each of those coordinates are, and then plug them into the function. So the function given to us here, now a real function isn't given to us in terms of f of x, y, but what is given to us is a contour map. So we can use that to find the value of each xy ordered pair. So once again, we have f of the first coordinate, let's pick this one here, that's going to be 1, 1, plus f of, right here, this is going to be at 1, 3, plus f of, over here, that's going to be 3, 1, and then we have plus f of 3, 3, as shown right here. And then we're going to multiply that by delta A. And delta A is going to be the area within each smaller square. So obviously all the squares, now it's not drawn obviously into scale here, and so each square has a width of 2 and a height of 2 as well. So 2 times 2 gives us 4, so that's going to be the area. So we're going to multiply by 4. So now if we go ahead and switch over to the contour map here, so now we need to look at f of 1, 1 and what value that is. So 1, 1 on the contour map is somewhere around here, and that's sort of in line with the value of 30. So we can estimate that f of 1, 1 is around 30. So remember, this is just an estimate, not an exact value. So we have plus, now f of 1, 3. So 1, 3 on the contour map, be around here. Now this is sort of in between 0 and 10, but closer to 0. So let's just say it's around 1. So plus 1, now plus, here we have f of 3, 1. So f of 3, 1 is going to be here. That's exactly in line with the value of 10. So f of 3, 1 is going to be 10, plus f of 3, 3. Now if I look at 3, 3, it's around here, between 0 and 10, but closer to 10. So let's go ahead and say it's 9. So 30 plus 1 is obviously 31. 31 plus 9 is 40. And 40 plus 10 is 50. So we get 4 times 50, which gives us a value of 200. So we can go ahead and say that the value estimated is around 200. So now I'm going to move on to part B, where it says estimate the average value. Now before I do that, I'm going to go ahead and put the 200 up here to say the integral, or the double integral, is around 200. Now there's a formula for the average value for double integrals, and so the average value formula, let's call it f sub average. So that's going to be equal to 1 over a of r times the double integral of f of xy dA within the region R. Now the formula for the average value of a double integral is going to be f sub average equals, now it's going to be 1 over a of r times the double integral described by the region R of f of xy dA. Now a of r describes the total region described by R. So in this case, the entire contour map is going to be the area. So if it's a 4x4 contour map, then the area is obviously 16. So a of r is going to be equal to 16. Now we've already found, the good thing is we've already found the double integral to be around 200, so we can use the midpoint rule to approximate the average value. So in this case, the average value, so f sub average, is going to be equal to 1 over a of r, which is 16, times our estimate of the double integral, which was 200. So then we get 200 over 16, or 100 over 8, or 50 over 4, and then 25 over 2. That leads to a value of around 12.5.